So the next thing we're going to take a look at with respect to graphing 3D surfaces are these quadratic surfaces. Quadratic surfaces, first of all, make very nice shapes that we've probably seen in 2 dimensions before. And unfortunately, the equations are generally fairly large to manipulate. Okay, so we have this general form that very rarely are we going to use, but just to kind of identify what it is. You have 3 quadratics, a, b, x, y, and z. You have 3 linear, xy, xz, yz. You also have these linear terms, and then you have a constant j. And what that produces is that produces one of the 6 following quadratic surfaces. Now, the way I try to classify these is I think of them as group 1 and group 2 types of surfaces to help distinguish which one's which. Group 1 is the stuff that's on page 1, and that's where you can write the form as something equal to 1. All right, so what I want you to notice is that in each of these types of shapes, they're equal to 1. All right? So if you can somehow set the equation equal to the constant 1, then you know you're dealing with either an ellipsoid, a hyperboloid of 1 sheet, which is basically a cylinder that's been smashed in the middle just a little bit, or a hyperboloid of 2 sheets, which looks like the hyperbola except in 3 dimensions. Right? So another thing to note is how to differentiate between the ellipsoid, hyperboloid of 1 sheet and 2 sheets, and all you have to do is just take a look at the number of positive and negative signs. So for the ellipsoid, these are all positive. For the hyperboloid, you have 1 negative, and for the hyperboloid of 2 sheets, you have 2 negative. Right? If all 3 of the terms are negative, then you would just multiply by -1, and hopefully you can equal a positive value. If not, then that surface doesn't exist in the real numbers. Also, let's think about how these would expand. And so when we say expand, we mean which axis is this shape going to get larger upon. And if you look at the subtext, especially for the hyperboloid of 1 sheet and 2 sheets, for the one that has hyperboloid of 1 sheet, whichever coefficient is negative on the left-hand side, that's where the hyperboloid is going to expand. Over here, whichever one is going to be positive, that's going to be the axis for which the hyperboloid of 2 sheets expands upon. And we know with an ellipsoid, there's no expansion. It's just basically finding intercepts and then tracing that ellipsoid. Notice that if all 3 of the coefficients are the same, A, B, and C, then we're dealing with a special type of ellipsoid called a sphere. So that's page 1. Now page 2, this is where you could set everything equal to 0. So if you can set it equal to 1, it's page 1, type 1 on page 1. If you could set the quadratic surface equal to 0, that's a page 2. A cone, x squared plus y squared minus z squared equals 0. All right? And notice that you have 1 negative, and the cone expands upon the coefficient that's negative. All right? So it's not always the z-axis. So if the y were negative, it would expand upon the y. Notice that all of these are quadratic. We have it equal to 0. All right, and we have 1 negative. All right, now, the elliptic paraboloid and the hyperbolic paraboloid both have one of the terms as linear. Okay, so we have to have exactly 1 linear term. Right? The axis of expansion is going to be the one, or is going to be the axis to where that variable is linear. And the only difference between the elliptic paraboloid and the hyperbolic paraboloid is that the elliptic paraboloid, all the terms are positive. In the elliptic paraboloid, 1 term is negative. All right, so One of the first exercises I want to look at is trying to take all of these items and just going through and seeing if we can identify shapes if you're given the equation. And sometimes we're going to have to rewrite these so that we can fit it into the form. So let's go down here. And we have a variety of shapes. In fact, we have all 6 shapes, and we have 6 equations. And it's our job to be able to match the equation with the shape. Some of these are extremely easy. Okay, so for example, let's take a look at some of the easier ones. All right, one of the easiest ones I find is to start with the ellipsoids. All right, so let's start with C. And remember, an ellipsoid is all quadratic. We have it set equal to 1, and all the terms are positive. All right, and that's really easy to see that number 1 fits the ellipsoid definition perfectly. Okay, so if I was to match this up, letter C would be equal to equation 1. All right, so that gets rid of this one, and it gets rid of that one. All right. Another one that might be easy for us to find is where we have when we start having some of the linear terms, so we can get on to page 2. So let's look for examples to where we have a linear term, and one of them is number 5, and another one with a linear term is going to be number 6. And of course the question is, which one is which? All right, so number 5, we can rewrite this. We can rewrite it as 4x squared plus z squared equals 4y, or x squared plus 1/4 z squared is equal to y. All positive. We have one linear term. Right? And so if we go back up, this looks like an elliptic paraboloid. All right, so it's all positives. All right, so and except we have that y is equal to this. We should also note that this should expand on the y-axis. All right, because that's the isolated variable. So let's see if there's an elliptic paraboloid, and let's see if there's one that expands on the y-axis. And it looks like right here, for letter D, that looks perfect. Right, so we have an elliptic paraboloid, it expands on the y-axis, so we can say that letter D is going to be equal to equation number 5, and we can get rid of equation 5 now. Right. I'm going to clean this up just a little bit since we have several of these to work through. All right, so now we could just cheat at this point and not do any work because we know that there's only one other quadratic. Or we know, that there's only one linear term, and that's going to be the hyperbolic paraboloid. All right, so we could probably see right away that 6 is going to be equal to a, but let's verify that. All right, so let's isolate the 4z. So we would get 4x squared minus y squared equals negative 4z. We're going to divide by negative 4, so we're going to end up with 1/4 y squared minus x squared equals z. So we have a linear term. I'm just going to borrow this. So we have one linear term. We have one negative, and it should expand on the z-axis because z is going to be the variable that has that linear term this time. All right, so if we look back up here, well, clearly that's going to be the hyperbolic paraboloid because it's the only other one with a linear term, but it should expand upon the z-axis, and this one does indeed. Okay, so notice that this shape is going up on the z-axis, so that's how we know we actually have the correct one. Okay, so for number 6, that's going to be equal to a. So we're mowing through these. We have this one down. We have this elliptic paraboloid down. All right, so we're done with this one. Probably the next easiest one to work with is probably going to be y squared equals 4x squared plus 9y squared. All right, this one's a little sneaky, but we know that we could set that one equal to 0. All right, so let's rewrite that one. I'm going to clear out some of this stuff here. All right, a little bit more down here. That didn't work out too well. Well, regardless. All right, one last try, and we can just erase. All right, so we're going to work on this y squared equals 4x squared plus 9y squared. Let's subtract 4x squared and 9y squared from both sides. So we have y squared minus 4x squared minus 9z squared equals 0. If we were to multiply through by -1, 4x squared plus 9z squared minus y squared equals 0. So we have all quadratic, we have it equal to 0, and we have one negative. So right away, because it's equal to 0, we know that we're going to have a type 2 or a page 2. So I'm going to go up here, look at page 2. They're all quadratic, equal to 0, and we have one negative. Notice that the variable whose coefficient is negative is going to be the axis of expansion. All right, and so we have a cone. Axis of expansion is the y-axis. So it looks like right away that it does fit the criteria we're looking at. So number 4 is going to be B for us. All right, almost done with this. So the last two that we have is we're going to have, I got rid of the ones we already crossed out, but that's okay. Nice and easy. So we did 4, we did 6, we did 5. So the only ones we have left are 3 and 2. Number 2, we could just divide by -4, and we would wind up with one positive on the left and 2 negatives. So that would be y squared minus 15/4 x squared minus another 15/4 z squared is equal to 1. So we have 2 negatives equal 1, so that should be on page 1. Axis of expansion should be the y-axis. So 2 negative equal 1. All right. Clearly this is going to be the hyperboloid of 2 sheets expanding on the y-axis. So we know right away that 2 is going to be equal to E. Right? And then by default, the only one we have left is F. And F is going to be equal to 3. And that's pretty obvious because we have 2 positives. We have 1 negative. We could divide by 4. And so we would end up with, if I was to write this over here, just to put it into the form that we can easily see, that would be x squared plus z squared minus 1/4 y squared is equal to 1. So we have 1 negative, it equals 1. All right, so it should be expanding upon the y-axis. So we have this hyperboloid of 1 sheet, and again, that is expanding on the y-axis. So we know with almost certainty, unless we made a calculation error, that number 3 is F. All right, so that's how you can try to decipher each of these. You're going to use this sheet, and this sheet's going to be very helpful for you to be able to identify some of these quadratic surfaces. In the last video, I'm going to give you the equation, and you're going to be able to identify the surface as well as some of the key characteristics, and this table is going to be very useful for that.